All right, so in this video, we're going to talk about linear differential equations. Now, in the past, we've talked about separable for the most part, but now we're going to change it up. A different type is a linear differential equation now. And one of the most important parts of solving these types of differential equations is being able to recognize them and get them in the appropriate setup. So the appropriate form that we're going to need to start with every time is going to be the dy dx. Note that there is no coefficient in front of that. And then we have plus a function of only x followed by a single y equals some other function of x. So we must be able to get into this form precisely before moving forward. Now, to solve these linear differential equations, we're going to use what's called an integrating factor. The integrating factor for this particular type of differential equation is going to be e raised to the integral p of x dx. And that's another reason why finding that p of x very, very carefully is going to be important. Okay, so I'll go ahead and clear the screen. We'll take a look at an example. You'll probably appreciate the mechanics behind this. There's not as much guesswork needed as sometimes with separable stuff. But either way, it is a new type of differential equation, and we'll go ahead and take a look. Okay, so here we go. This is our first linear differential equation, and you can see for the most part we are in the correct form. We've got our one coefficient here. We do have a minus y, so we might want to be a little bit careful with that and view that as a plus a negative 1 times y. Now you certainly don't have to write that, but that's how we're going to view it for now. And then equals some function with respect to x. We're also given an initial condition here, which is going to allow us to solve for c at the end. All right, so now to get started, we're going to use that integrating factor that I pointed out, which is going to be e raised to the integral of, in this case, a negative 1 dx. And so when we integrate this, of course, we get our e to the negative x. I'm not going to worry about the plus c. You'll see the plus c tacked on at the end, and we'll actually be able to solve for it as well. So that would be our integrating factor. Now, the next step is to take this integrating factor right here and come back up to the original, and you're going to multiply both sides by the integrating factor. Okay, you're going to take this equation here, you're going to multiply both sides of it by whatever integrating factor you came up with. So when I do this now, this gives me an e to the negative x dy dx minus a y e to the negative x equals 11/8 e to the negative 4x over 3. So when I combine, I've got one of them here, I've got negative one of them, and then I have a negative 1/3 of them to get a negative 4/3 of them. Okay? Now, the next part is actually pretty interesting. We're actually going to reverse engineer this derivative product rule. All right? Now that sounds like a mess, but it's really not too bad. This guy right here is always going to be y times the integrating factor. All right, now when I say y in this case because it's the dependent variable. So obviously if these are different, it's not going to be a y. But in this case, because y is the dependent variable, and we've got a dy dx here, it's going to be y times the integrating factor. Okay, now you might think that sounds crazy, but trust me. If we now take a look at this, I'm claiming that this guy right here is this guy right here. Well, if we do a product rule here, derivative of the first times the second plus derivative of the second, which would be e to the negative x times a negative 1 back times the first. So that guy right there is the expanded product rule for this product right here. And that's where the integrating factor comes from. That's what's going to allow us to create this setup right here. Okay? Now, on the right-hand side, nothing has changed. That's just an 11/8 e to the negative 4x over 3. All right, so now we're to the point where we can actually integrate. So in your mind, view this dx as being moved over here, and then we'll go ahead and integrate both sides. On the left, that and that are opposites, so that's gone. And then the dx, remember this guy, has been moved over. And so we're integrating this now with respect to x. All right, so on the left, we'll have this y e to the negative x. And on the right, we're going to have this negative 33 over 32 e to the negative 4x over 3. And then I'll go ahead and tack on the plus c there as well finally. Now this is one where we can actually solve for y pretty easily. And so to do that, I'll go ahead and divide everything by e to the x. So in doing so, we have our y equals negative 33 over 32. This is now going to be e to the negative x over 3. So if I divide that, and then I can go ahead and flip it back around and combine, and then plus c times e to the x. All right, so again, all I did going from that step to the next one was I multiplied by 1 over e to the negative x. All right, so here we go. We're looking now at our general solution. To find the particular solution, we'll go ahead and use the initial condition. Y of 0 is going to give us a negative 33 over 32 times 1 plus c times 1 equals 0. So c is going to be a positive 33 over 32, giving us for our final answer now a 33 over 32 e to the x minus 33 over 32 e to the negative x over 3. So as far as the using the initial condition goes, nothing at all is different there. However, obviously to start this thing out, we needed to make sure it was in the correct form. The integrating factor then, when once multiplied back through, gave us the ability to set this up. We'll take a look at another example and I'll show you again how it's going to work every time. But from there, then it's just a matter of integrating and working your way through the problem as always. Okay, so for this next one, it's going to be a lot of the same stuff, but I chose this one for a couple of reasons. First of all, I'm using different variables. X's and Y's are great, but for a problem like this, it's really important to understand independent versus dependent variable. So when we put this back together, it's going to make more sense. Another reason is because this one's going to require us to simplify a bit more before we can move forward. Remember, this coefficient has to be a 1, and this has to be a plus, which it is. Now, I'm going to go ahead and to create this, or to essentially take this away, I'm going to divide everything by t natural log t. So that's going to give me a dr dt plus 1 over t natural log t times r equals e to the t over natural log of t. Now, for the most part, what you see is pretty self-explanatory. But it should be pointed out that I wrote it a certain way for a reason. It's important to note, remember, r is the dependent variable here, and so I've got my function of t out in front of the single r there, and then I've got my function of t over here as well, with again that coefficient being a 1 now. So by writing it this way, it's going to give us the opportunity to use our integrating factor, which is going to be e raised to the integral of 1 over t times natural log of t dt. Now, this integral I'm not going to work on the screen. It's a simple u sub, let u equal this guy. It matches perfectly with our du, etc., etc. But that ends up giving us e raised to the natural log of the absolute value of the natural log of t, in which case the e and the natural log can do away with one another, leaving us with just the natural log of t. So there's our integrating factor. And just like the last one, we're going to take this integrating factor and we're going to multiply, whoops, not there, multiply both sides of this guy by it. Okay? And so the reason the integrating factor is what it is, it's going to allow us to multiply and then create that product rule on the left-hand side. So when I do this now, I get the natural log of t dr dt plus 1 over t times r equals just an e to the t now on the right. And so now we're ready to put together, reverse engineer, if you will, this product rule. And the last example, I said it's y times the integrating factor. Well, now we don't have any y's. In this case, our dependent variable is going to be r. So it's going to be r times the integrating factor. So r times the integrating factor, and it's going to be d dt. So again, let's follow me on this. That we've got a product rule. Derivative of the first times the second plus derivative of the second back times the first. So it does in fact work the same way again. The integrating factor is doing this for us and will continue to do it for us every single time. On the right hand side we have e to the t. We're now ready to integrate. On the left we have this r natural log t. On the right, e to the t plus c. And then to solve for r, we will have the e to the t plus c all over the natural log of t. So there's our general solution to the linear differential equation.